Welcome back everyone. In this lecture we will continue with the properties of universal unpairing algebras. So, we will actually state very main important theorem on these algebras called Poincare-Birkhoff-Witt theorem. So, I am actually going to give only partial proof. So, we will actually complete the full proof later when we have time. Okay. Because the statement of this theorem is more important, and of course, the ideas are also important, but in some different context. Okay. So, let us actually just give some motivation for this theorem. So, let us actually look at the symmetric algebra associated with G. So, take G to be Lie algebra. Now, we can just assume to be finite dimensional Lie algebra, there is no issue. Let us say we have basis x1 etc. xn. So, this is basis of G, where n is the dimension. Okay. So, we can actually take the symmetric algebra. So, which is by definition you take Tg and then go modulo two sided ideal generated by x tensor y minus y tensor x, where x and y comes from G. Okay. Then we have already seen that this is naturally isomorphic to the polynomial algebra generated by these variables xi, x1 etc. xn. So, here in this polynomial algebra we assume that x is commute. Okay. This is commutative C algebra. Now, if you think about it, there is a natural basis of this which is given by xi1 etc. xik, where these I1 etc. ik they all come from 1 to n, such that since all the variables commutes, I can arrange it so that I can arrange it in the increasing order. Okay. So, these elements will form a basis. So, this is actually very easy to prove. Now, you can ask that, okay, if we go to the universal unpairing algebra, so when G is abelian, then UG is same as SG. Okay. In that special case, we have such very nice basis. But if you take general G, then recall what is UG. So, UG by definition, you take T of G, go modulo two sided ideal generated by x tensor y minus y tensor x minus the bracket xy, where xy comes from G. Okay. But it is somewhat very close to SG. Okay. It is not too far from SG. Only thing is the bracket of xy is being 0. So, G is abelian, then SG and UG are isomorphic, but G could be non-abelian. Okay. The cases that we will be interested in only SL and GLN, they are highly non-abelian. But what are the relations that we are going modulo? Just look at the relations. The relation says that whenever you commute the variables x and y and you are paying a cost, that cost actually given by lower degree terms. Okay. Whenever I commute x y and then write it as yx, okay. Let us work in the UG itself. Let us denote x tensor y as xy inside your universal unpairing algebra. So, you have this map pi under the image, the tensors just written as product, okay, as in the SG. So, there is no confusion here. Now, whenever you commute these variables xy equal to yx, then you are saying that they differ by just this extra element plus bracket xy. But the thing is, this element indeed comes from G. Okay. So, basically we are working in the images. Okay. So, I am just not using this iota of x, but I am identifying iota of x with x. Okay. But let us, okay, if you are not comfortable, maybe like let us do it with iota. So, basically this is iota of x and iota of y. So, iota of x, iota of y, when you commute them, then you are paying I out of bracket x y as your cost. But this is definitely lower degree term, because that comes from the image of, because it comes from the image of G. Okay. So, now because of that, you can see that if you are taking any element inside UG that spans, okay, you can take any k tensor and then look at the image of the k tensor for any k, that will be the spanning set for UG. Okay, that is easy to see. So, UG is spanned by, you can take all possible xi1 etc. xik, where now k can be any non-negative integer such that only restriction is I1 etc. ik should come from n. So, this is definitely a spanning set for UG. But then now the question is, can we arrange this in some increasing order? Okay, now the question is, can we arrange these words in the increasing order? Okay. And Poincare-Birkhoff theorem says that it can be done, and that will again give you basis for your UG. Okay. So, here is the PBW type basis. So, you can always arrange, you can take iota of xi1. So, maybe let us call them as yi, iota of xi to be yi. Okay. So, then you can take yi1 etc. yik, the product where k is greater than or equal to 0 and I1 etc. ik, they all come from 1 to n. So, we can just simply write 1 less than or equal to I1. You can always arrange them in the increasing order, so that this form a basis. So, this set form a basis for UG. Okay. So, the basis of UG very much look like the basis of HG. That is what PBW theorem says. Indeed, one can write very much equivalent statement which says that, okay, maybe I will just state it, I will leave it as exercise. If you know the construction of graded algebra, then it is easy to see that the graded algebra associated with UG, because we already seen that UG is a filtered algebra. So, there is a graded algebra that one can associate with UG, that will be naturally isomorphic to the symmetric algebra associated with G. So, in particularly if you take the graded piece, kth graded piece, that will be same as the kth graded piece of this SG, and then as long as you are actually taking the graded algebra of filtered algebra. So, there is this natural way of identifying basis of UG with the basis of the graded algebra associated with UG, okay, grade UG. So, that is why you are actually getting somewhat look-alike basis here in the UG. That is what PBW theorem says. Okay. So, I will actually prove only that this set will form up, this set will be spanning your Lie algebra. Okay. So, we will come to this proof of linear independence later. Okay. That is somewhat bit involved, but if we need that idea, maybe we will come back, otherwise we can actually skip that result. So, how one can actually think about arranging them in the increasing order. So, if you just really actually take this word, okay, y I1 etc. yik, if it is in the correct order, that means if it is in the increasing order, then there is nothing to prove. Okay. Let us say actually you are reading it from left to right, and then at some point the order is actually misplaced. Okay. So, let us say the very first instance where it happens, call it rth position. So, then you have y I1 etc. y r minus 1, which are indeed in the correct order, and then when you go to y I r, y I r plus 1, they are not in the correct order. So, these two elements, they are not in the correct order. So, then how do you actually kind of make them in the correct order? For example, like it can be 5 and then 3, but somehow you want to switch them and then make them in the correct order. How one can do that? Of course, we can do that because whenever you switch, you are only paying some element which are actually coming from the lower degree term. So, what does it mean? So, then this is exactly equal to, so y I1 etc. y IR minus 1. So, we can switch this to yr plus 1 and yr, and then you can write all other elements as it is. So, now if you think about it, yr plus 1, this is exactly equal to yr plus 1 yr plus there will be lower degree terms. Okay, it will be a bracket first of all, bracket yr plus 1 and bracket yr plus 1, that is going to be there in your Lie algebra, image of the Lie algebra iota of G. So, that means the bracket yr plus 1, it is written as some summation, some y, let us say Lj, where a Lj appears here, or you can just write it in yj, aj, yj, j range from 1 to n. Note that yj is nothing but the image of I, okay, image of xj. So, you have switched here, then you have to pay the price, because this is what you are rewriting. So, now you pre-multiply and post-multiply by these words. So, you multiply by this and whatever is here. So, this is call it A and then B, then you multiply here A, B and then again A, B, and here you will be having A, B. So, here A, B and here again A, B. So, that means this is exactly gives you summation A j A y j B. Okay. But note that these terms, they are lower degree terms, they are lower degree terms. Okay. So, by induction on the length of the word, okay, lower degree means lower length also you can say, whatever the degree means. So, then you can see that by induction on the length or the degree, so you can assume that that is already there in the span of these elements. So, you want to prove that, let us call this as S. So, this set S spans your UG. So, that means by induction you can assume that, so these elements are there in the span S. Okay. So, now what we have done, so in the very first instant where the order is not correct, we could switch and then we can write it as some lower degree terms which are there in the span S. Okay. So, now if you take this particular word, again you can do the similar thing, you can read it from left to right. So, up to rth position, actually r plus 1th position, the order is correct. So, then from r plus 2 position, whether order is correct or not, you can read it again and then see. Then you can see that if it is not in the correct order, then you switch back. Okay. Then again you will be paying some cost, which will be sum of some lower degree terms. So, now by induction we can prove that any given word indeed is there in the span of S. Okay. So, that completes the proof that span of S is exactly UG. But it is not that easy to prove that it actually it is linearly independent. Okay. So, we have to actually construct some representation of UG, because UG, so the motivation indeed comes from this. Okay. So, UG is naturally going to act on the graded algebra associated with VG, that is in particular on SG. So, using that action you can actually prove that because this SG is being very big infinite dimensional space, UG is acting on that will be like is going to give you like large representation. Using that representation you can actually prove that these elements will form a linearly independent set there. Okay. So, what is the idea behind that? Let me just state the idea at least. To prove something is linearly independent. Okay. To prove S is linearly independent, okay, construct a large representation of UG. Okay. So, that means you have a map from UG to this representation, let us call it endomorphism of V, where V is practically speaking it is a infinite dimensional representation. Okay. It is an infinite dimensional thing. So, now we can just assume it to be vector space over C. So, now look at elements x coming from S and look at phi of x. Okay. So, now what you can do, like to prove that phi of x they are all linearly independent. Okay. So, you can make this phi of x act on some particular vector. Okay. In the case of UG, you can take the unit element inside SG, you make it act on that. But then you can say that you are fixing some vector V naught, okay, fix this and then make phi of x acts on this V naught. Okay. Suppose if we have a relation summation AI xi is 0, then that would imply that summation AI phi of xi is also 0, and that would imply that summation AI phi of xi acting on this V naught will be 0. So, now you can easily see that if phi of x V naught, this set is linearly independent, then that would imply that AI's are all 0 for all I, and that would imply that the set x in S is linearly independent. So, this is the idea to prove that any given set is linearly independent using the representation theory. So, you have to construct a big representation and then you can make all the elements of UG to act on this vector space and pick a very nice vector, so that when you act it using all the elements of this S, that set will form a linearly independent set inside capital V. Okay. So, then that would imply that the original thing that you started with will be linearly independent. So, that is the idea indeed used in order to prove that this set is indeed linearly independent. Maybe like I will do this later. So, now what one can do actually, one can actually focus on only the SLN representations and then try to see that how one can construct some important elements in the center of the universal Olympic algebra. Okay. So, first of all let me define some of the terminologies. So, let us call it the center to be the Z of UG. So, this is just the center of UG. So, by definition this is those elements x in UG that commutes with all the elements. So, xy equal to yx for all x in UG. So, this is the usual definition that you see in group theory or algebras. Okay. So, and then it is immediate that the center is indeed subalgebra. Okay. This is a C subalgebra. So, UG is is an associative algebra with unity, and the unit element commutes with all the elements of UG. So, in particularly this is associative C algebra with again 1, okay, that is most important, and that is easy to prove. Only the product you have to check that it is there closed. So, if you take x1 x2 inside the center, then the product x1 x2 again commutes with all the elements of UG. So, that is easy to see. So, now if you have some irreducible representation, you can easily see that any element of the center indeed acts as scalar on that representation. Okay. So, that just follows from the Schur's lemma, but then that kind of like, so we need to have some guarantee that, okay, the center is always non-trivial. So, that is why we need the construction of this Casimir elements to ensure that this center is indeed non-trivial. Okay. But the thing is, one can actually prove this is the theory of Harishchandra. So, he introduced what is called central characters. So, using this theory of central characters, one can prove that this center of the universal enveloping algebra of a semi-simple E algebra, so that is indeed really big. So, it is a polynomial algebra. Okay. So, one can prove if G is semi-simple, so then the center of the universal enveloping algebra is a polynomial algebra, and of course, how many variables you can say of n variables, where n is the rank of that G. Okay. If you take n to be the rank of G, which is the dimension of the Cartan subalgebra, so then you can see that it is a polynomial algebra in n variables. So, it is not something very small for semi-simple algebra. So, but that actually requires this central character theory to prove such statement. It is actually very non-trivial statement. But what one can do, like for all our basic purposes, okay, for example, we are interested in proving Weil's complete reducibility. For that purpose, it is enough to actually produce one non-trivial element inside your center. Okay. So, that is what Casimir element construction actually gives us. So, let us actually try to construct the Casimir element inside your the center. Okay. So, let us actually just assume G to be epsilon, okay, for the rest of the lecture. So, recall that the killing form is indeed the non-degenerate form. Okay. The killing form. So, what are all the property it has? It is G invariant, symmetric, bilinear form. Okay. This is also non-degenerate bilinear form or epsilon. Okay. So, now if you fix a basis, whatever you can actually take the standard basis and then try to compute what will be the dual basis of that. But anyway, if we take any basis x1 etc. xn, let us say n is the dimension of G. So, this is the given basis. Then we can talk about the dual basis of this with respect to the killing form. So, let us call this as beta, dual basis with respect to beta. So, this is y1 etc. let us say yn. So, that means it is defined as follows: beta of xi yj is given by delta ij. Okay. So, now we can define the Casimir element with respect to this pair. Let us call it C, that is summation xi yi, I range from 1 to n. Note that this is we are taking inside UG, I am allowed to take product of elements of G inside UG. So, I just take this products and then take the sum, which is well defined element inside your UG, and this is called Casimir element. Okay. The most important thing is this Casimir element lies inside the center. So, this is the climb, the C lies inside the center. That means C commutes with all the elements of G. In particularly, it defines, for example, map from any representation to another representation as a G module map. Okay. If V is a G module, then I can define a map from V to V, we can call it C. So, you take the vector V and then send it to the summation. Okay, I am just dropping this iota notation, but you can always use that. But now you can see that using the PBW theorem, okay, the map, the G to UG, that we have this iota map, this is indeed injective map, because the images of G indeed lies inside the basis of that we constructed in the PBW basis theorem. So, then naturally this map becomes injective map, because if it is not injective, then there will be relations. So, that will actually give you relations on in G itself. Okay. So, in particularly I can just simply denote iota of x by x, there is no issue. So, we have this vector V, we can just send it to xi y acting on V, where I range from 1 to n. So, this is the map we are considering, and this map you can see that commutes with the action of G, because it is there in the center of UG. So, it defines well defined G module map. So, that is the use of this. In particularly, if this map is non-zero map on given irreducible module, then you can easily see that that must be acting as a scalar, because that is what Schur's lemma says. Okay. So, let us actually prove this, this is indeed lies in the center. Okay. So, we need to make following observations. So, there are two observations you need. Observation 1 is that if you write some element x in G and then write in terms of the basis, okay, write the bracket x xi to be summation a I j x j, and then write again x y I to be summation b I j y j. So, then we can easily see that using this associativity that we have the following observation a I k. So, this is given by, so which is same as which is appearing inside this summation a I j. So, this is going to be summation a I j. So, you can take it to be, because the kappa is going to give you delta I j. So, this is exactly the kappa of G x j y k, because this is just a delta j k. So, whenever j equal to k, you get a I k. So, that is why you get this. So, this is exactly equal to kappa of G the bracket x x I comma y k. So, now this says that a I k is exactly equal to kappa of G. So, you can just switch them. Okay. So, then this is exactly x I. So, you just switch this minus bracket x I x and then use the associativity or the G invariance. Then this is exactly x I comma minus the bracket x comma y k. Then if you just rewrite this, this is summation b k j kappa G and then x I y j, okay, where again j runs over this. Now, note that this is again delta I j. So, whenever I equal to j, it survives, otherwise it is 0. So, this means this is exactly aik is exactly minus bki. So, this is what you get as first observation. So, now let us look at the second observation. Okay, if you put them together, you will get the result. The second observation is that, and this is true for any endomorphisms. So, you take 3 endomorphisms from any endomorphism of V being a vector space, then you have the bracket x, the bracket yz. So, this is going to be, because this type of elements only will come when you compute the bracket C x, where x comes from G. So, this bracket is exactly equal to the bracket x y z plus the bracket, so y times the bracket x z. Okay. So, this is very easy exercise, I will leave it as exercise. Okay. So, just check this. So, now if you use them, then you can easily compute what will happen to the bracket x c. Okay. So, let us compute for x in G. Okay. Let us compute the bracket x c. So, because x c is nothing but x c minus c x inside your universal Olympic algebra, but we can just do this computation. You can see that this is summation x, the bracket x comma xi yi. So, now just to use this identity, then you can rewrite this as summation I, the bracket x xi yi, and then plus summation over I xi times x yi. Okay. So, 2 summation you get. So, now the bracket xi you can just rewrite. So, this is going to be summation a I j x j y I, where I j runs over, plus summation again I j runs over b I j x I y j. So, this is just the definition of bracket x x I and bracket x y I. So, now if you just think about it, if you look at the coefficient x I y j, okay, so that, okay, maybe that other coefficient you can x j y I. So, that is you are getting here a I j, but here if you take that you get b j I. So, that is what you get. So, this will be the coefficient of this coefficient. Now, we already know that a I j is same as minus b j I. Okay. So, that means when you add them you will get 0, a I j plus b j I is 0. So, that means this sum is 0. Okay. So, this proves that C indeed commutes with x for all x in G. So, that means C is inside the center. So, we will actually use this information in order to actually prove the complete reducibility. So, I will stop here and then we will start the complete reducibility proof in the next class. Thank you.